Hello guys. First we'll start with some introductions. Just to as a refresher, so who are out of all of you who are computer science students? That's right. Who are from data science? That's awesome. Data science here. Our speaker is also from data science program, and he's also the vice president of GRIDS. We'll start with the some introduction about us, who we are. We are a data science organization at USC. We organize events like this, technical workshops. We also have a hackathon coming up and a social night. Probably you would have signed up for it, hopefully. Our focus is usually to help people who are not from data science but want to excel in data science, get some hands-on experience, probably participate in projects. Without the After this, let's me just show you this flyer which one of our marketing team person has made. Does it look nice? Yeah. That's all. Thank you. You guys can sign up for the event. This is the QR code. We also have flyers, so probably you can use that later. That's fine. Regarding Social Night, so it's one of our bigger events at campus, where we organize fun game events, and you can hang out with other people. It's a good networking opportunity. Also, professors who have taught data science usually come. One of our speakers is Sati. You must have taken his course. If you are at USC Computer Science. That's at HER 101. It's a little unknown building, but you can probably search it on Google. HER Harris Hall.
And free food.
So that's one of the other motivations. Yeah. Something about our speaker will be coming after this. He has 4 years of experience in data science. He has done a lot of diverse projects while working at United Health Group. He was an intern at Capital One. He'll be joining Capital One after passing out in May. And he has also worked at USC in EE department as research. And one of his, I think, probably he doesn't speak about it, but probably you can ask him about his Japan experience, where he went. And there are some fun stories which he can share, probably after the event. And so that's before. After this, let me ask Satwan who can join us. Yeah.
Yeah, so I basically attended this conference last year. So USC asked me to fly to Japan to represent USC. We did a conference, so that's how I landed up in Japan last. So I work in brief background of myself. I work in electrical engineering department in epidemiology lab. So we mostly work around COVID-19. Most of the research is around that. And in UHG, it's a healthcare company. So I worked with CDC and White House in 2020 when they actually started working the COVID-19 when it hit. So they had to do a lot of stuff around it. So we were in that as well. So now let's talk about why we are here. So how many people have actually worked with graph neural networks before? No one.
Maybe online. Online people.
Anyone online who has worked with graphs, neural networks? But we know about graphs in general, right? How the graph data structure looks like. Yeah, so graphs probably are everywhere. So if you see some sample examples here, like chemical molecule structures, brain neurons, networking information like planes and network information. That's a metro graph. It's also a graph. So a lot of optimization problems can be solved using graphs. So recently people started extracting a lot of information using graph neural networks, which is pretty new. So these are a few of the use cases in industry where people have actually used graphs. So in Pinterest, I actually worked on this project in Amazon when I was working last semester in knowledge graphs subject. So what they do is like in your Amazon login session, you click on certain things, those become your nodes in the graph, and then you end up buying certain things out of this session, right? So those independent nodes have actually the label as like purchased. So out of your network of like your history, Amazon is actually extracting like what are you interested in, and if I reroute your search if I show you a personalized website only designed for you, which I know that these are the points if I navigate a person to, he will land up buying this thing. So that's the mission of their approach for this particular thing. And then Uber uses it, and all of the big companies use it. And like even in like Reddit subthreads, if you have to extract like who will comment on whom and how will a thread become viral, that can be done using graph neural networks. And these are all just sanity things. Yeah, so if you see like in 2021 ICLR, like a big name in machine learning, they saw that there's a huge spike in research papers around graph neural networks. So it's evident over here as well that the keyword coming up in the research paper has increased in recently like 2 years, which means like a lot of people are actually working in graph neural networks. And it has actually become easy to work on GNNs, probably because of like these libraries like PyTorch and all those things, because they make it pretty easy for you to just start utilizing those. So they have a nice documentation around it. Okay. So how I started working on GNN is like I took a course here, DSCI 558, building knowledge graphs. It's also cross-listed in CSCI, I guess 563. So it's a special course offered only in fall by professors from ISI. Professor Jay Pujara, who is like a pioneer in knowledge graphs. So he has worked with Google, LinkedIn, Microsoft, Yahoo, and one more company I forgot. Like he has worked pretty much with every big company, and he leads knowledge graph research, knowledge graph center within ISI. And Professor Philip, who is from Netherlands, and he joined US a couple of years back in ISI as a research scientist. So they take this course, and that's where they teach us a lot of stuff around GNNs. And this is their slides, which I'm using. Okay, so let's talk about what a graph in general is. So a typical graph is like nodes, which are like these circles, and then they have edges. So the definition of edge can be based on a problem statement. Like if me and Mridul are connected on Facebook and we are talking about Facebook graph, then the edge represents friendship. And if there is no edge between like D and D, it means that these two guys are not friend at current state, but a machine learning task could be like through the graph structure, can I predict should D be shown in the timeline of E as like add me as a friend? So if there's a high probability that there should be an edge between D and E, then Facebook will just populate as like add me as a friend. So this is like one of the use case which you can think of. And then there are a couple of things which we can like solve using graphs. One is like you can embed an entire graph structure into a vector dimension, like a representation. Like a graph can be very complex, like which initially saw about like railway metro structure or brain neurons or chemical molecules. But those are like hard to interpret. But if you can represent them as like a continuous vectors, right, then it is easy to utilize any GPU or any computation to solve any of the underlying tasks. So yeah, so one of the primary assumption when you work with GNNs is like the nodes which are close by in the network are like similar to one another. Like that's called homophily. So it's like so see B and D and C are very close to A. It means that they are kind of similar to one another, and as you go away from A, it means those nodes are less similar to A. So that's the assumption. Because if everything is similar to one another, then no information can be extracted out of it. So that's the only assumption. And if we have to know about A, we will ask these guys B, C, D. And if you have to know about C, then we have to ask A. That's kind of like confusing, but yeah, that's the key idea. Like to know about a node, you have to ask its neighborhood. And like once you build the GNN, then you can solve a lot of things like friend recommendation we talked about, product recommendation which Amazon, which I gave the example of Amazon. Fraud detection, this is something I worked in Capital One using graphs around like merchant fraud, and then churn prediction, which is like if you have to extract like which portion of your customer base you are losing every now and then, so you can extract those kind of structures from your data. Yeah, so if we take an example here, if you have to predict anything around A, we'll ask B, C, and D. And then if you have to know about B, C, and D, then you have to ask A and C for B because those are like the direct neighbors of B, and C is like surrounded by A, B, E, and F, and so on. So this becomes your individual layers in the graph structure when you start building. So the high level idea, we won't go into the math of these a lot because then it becomes pretty boring. I'll share these slides afterwards so if someone really wants to know about this stuff. So the key idea is like you represent every layer as a representation, like a typical neural network, and then you pass in the information from one layer to another layer using some sort of aggregation strategy. So people generally use like, sometimes people use like max pooling or average pooling kind of way to aggregate information, and you can embed like a lot of complex things which we'll talk about when I show the tutorial. That you can use attention layers, convolutional layers to represent these structures. So the key idea is like you have to aggregate the message in within a layer, and then you have to transform that message as you pass from 0th layer to first layer and so on. And then these are mostly around computational things like a graph can be pretty huge. So to process in your local machine, you need to use small batch sizes and all this stuff. So that is thing. Then there are a lot of downstream tasks which you can solve. One is like node level prediction, which is like the example we took about Amazon timeline thing, the Amazon purchase history, that what are the things I will buy or not. So that is something can be a node prediction task. Other thing can be an edge prediction task, like if D and A are closely related to one another in a social media network, so that I send a friend, Facebook like friendship request or something like that. And then is like attribute level prediction is like sometimes we have to fill a lot of information. Like sometimes the information is missing. Like on Facebook, if you take an example, a lot of stuff is like private for yourself, but you can also predict a lot of things around like what is your nationality. You can predict it based on the things you like, dislike, the things you post. From that, you can predict your nationality and your political inclination. So people actually use this in 2016. There's actually a movie around it on Cambridge Analytica. They actually harness Facebook data to create graphs and identify potential people who are currently leaning towards Democrats but can be pushed towards Republican if you show them the right content. So that was done in 2016. So that was actually a GNN class. And then a graph level prediction. So people use this in COVID-19 a lot. So if you have like different molecules or potential vaccine structures, and you have to predict which of them are actually suitable in discovering antibodies. So you can lower down your search space by building a GNN and identifying potential molecules which like as a whole can be categorized as malign or benign. So based on that, you can then further research in the laboratory. Because initially, if you have like 1,000 different potential candidates, you have to work on each of them individually. But if using some machine learning task, you're able to reduce your search to only 20 or 30, then it becomes like a gain of 20x, right? So that's one of the ways you can think this out. Yeah, so these are the examples. Yeah, so node level classification tasks can be like classify papers and all those stuff. These are like examples. Most of this is like examples of how it can be done. There is another thing which I want to show. Next we'll talk about like the coding aspect of it and one of the use case where we use this. But before that, you just have to keep three things in mind. One is like how many neighbors you want to actually leverage while building your structure. Others like how many hops you want to take. Like in our graph structure, we took like 2 hops. But the more hops you take, more generalized your solution becomes, and it might dilute the solution. And how do you want to aggregate? So it's surprising like people use different aggregation strategies and they publish new paper that I used instead of mean aggregation. I use max pooling, and I saw a gain of like 2%. I publish it as a new paper altogether. So that's why you see like a lot of papers coming up in GNN. So there's actually a paper on this neural architecture search that what if you don't really know how many layers I have to add in my GNN, how many pooling layers should be there, should I use ReLU, should I use TANH and all those things. So people actually have done neural architecture search using genetic algorithm and Bayesian networks to actually identify, they take up all the possibilities, and within few epochs of training, they identify that this should be an optimal number of layers in your structure. So that you can use. There's actually a PyTorch utility around it as well. And then the last thing on theory part is like even the tabular data solutions like any tree-based algorithm and all those things are difficult to interpret from an industry point of view. And this is a graph structure. Like in industry, no one really takes actions unless they interpret it, right? So there was a challenge around GNNs that even if you're getting great predictions from GNN, but how do I trust it, right? Right? What is the reason this GNN predicted something like this? So people in Stanford, what they did is like they created a utility in PyTorch directly, basis which that it can give you an explanation of why a certain prediction was made. So it's again based on Shapley, which is the game theory method. So what they do is like, so imagine if there is a graph like this one, and then a prediction was made, then what they will do is like recursively, they will get rid of edges and nodes to see if there is a change in probability which was done or not. So based on that, they identify a subgraph which is capable of generating almost same prediction, but it is interpretable. Like from lesser number of nodes, you can actually interpret why a prediction was made. And then like if someone has trained a model on Facebook, you can directly transfer that learning into a simpler task. Like people have to identify in research papers that who is the next author of my paper, who is the next co-author of my paper. That can be easily predicted using JNNs, because based on history of what is working on what and whom I have initially worked with becomes my network, and then I can just predict on like who will be my next co-author. So these are the examples I gave initially, like molecule structure, classification task. Like if you have to use a molecule as input and using GNN, you have to tell that if this certain molecule has a like any trace of E. coli, it's like a drug. So this is the theory part. So before we actually go to the PyTorch tutorial, any questions, anything you want to share, or any ideas you gathered on like, oh, now I know about GNNs, can I do this or something like that?
Is the node representation within each layer the same for the node, particular node, or does it change between layers?
Right. So in this task, if your solution approach is to predict something around a node, like a label of a node, then when you train the model, you take each node as an individual target. So then you see like in the first layer who are the neighbors, and then the node itself can be one of the inputs, right? So that's how it is.
So can we directly plug and play? Like we already have a model with CNNs. Can we directly plug and play?
Yeah, so the way this PyTorch geometric library has been made within PyTorch is like they have a lot of predefined collab notebooks. So they say it like a basic node level prediction task, a basic graph level prediction task. In that, you can just understand the structure of how the input was fed, and then you can just replace your input data set. Because if you start writing your own boilerplate code, then it becomes a bit challenging. So they give you like a defined class that this is the GNN structure. You can keep on adding layers to it or purge layers, and then you can see the accuracy and all. So I just to give more context, I'll show you guys one thing.
Oh, guys, please feel free to have some. No, zero. Zero. Something. The red one.
Yeah. Is it rated?
We good?
Yeah, I think we can do it.
Yeah.
So this actually is a slide from one of the projects we did. So we built a job search engine last semester, which we quote is better than LinkedIn in some capacity. So do you guys find LinkedIn useful when it comes to recommending job IDs?
No.
Yeah.
Sometimes.
Somehow.
So what's the drawback you find in the LinkedIn? Like are all the jobs relevant to you?
It gives me senior positions.
Exactly. So it doesn't do a good job at that, right? So what we essentially did is like, so we scraped entire LinkedIn last semester, like 40,000-50,000 job IDs using Selenium. And what we did is like, so every job description can be represented as a graph structure, right? So it has a bunch of skills within a job description, and they have a certain frequency with which they occur, right? And then there is a co-occurrence frequency of each of the pair of skills which occur, right? So then you can represent a graph out of it. So the assumption here is like as it becomes a senior position, we kind of duplicate the content in that capacity to amplify certain attributes. So we kind of represent every job description as a graph of skills. Like this is a sample JD which has like Python, Java, and SQL, and then this is their like term frequency and in Word document frequency as the features, and then the edge feature is like the co-occurrence frequency of these like Python, how frequently like Python and Java come together across like their own individual frequencies, which is like mutual information formula. So similarly from your resume as well, you can pass in all the information, and then you can make a graph of your resume. And then if you train a GNN on the job descriptions first, and then you compute the similarity between the representation of a job description, which is essentially a graph, and your own resume, which is also a graph. The more similarity it is, like it's more likely you are a good fit for that. So then we did like a pilot with like 10 people. We asked them to like compare like the results coming from our solution and LinkedIn. So that's how we like kind of evaluated the solution. So the whole idea is like anything can be translated into a graph, and then you can generate better result as compared to any tabular data approach or something like that. So like if I quickly show, yeah. So we just treated every job description as individual graph, and then we trained GNN using attention and GCN layers, and then we extracted the penultimate layer, which is like 128 dimension vector representation.
Quick doubt. So I'm comparing this architecture to something wherein using TF-IDF just generate a vectorized form of all the skills that you have and you don't have, and then I employ a classification task on this data to identify whether I should recommend the job or not. So
Correct.
how do we compare to that? I do get it that graph
Yeah.
will be better. I'm not able to imagine how it is modeled as a graph.
Right. So sometimes occurrence of two skills together make a job specific to something. Like if I have skills from both full stack, like back end and front end, then it kind of appears as a full stack job description, right? But on the label of the job, like these recruiters, they don't put as like full stack. They will put as software engineer, right? To harness that information, you need to tell the solution that occurring of these two means something, right? Unless you can just make it like an encoded vector, right? Binary, occurred or not occurred. But yeah, here we are also trying to capture like how many times did it occur and all those things. And this was like the accuracy and all the stuff. So we try to generate results for 7 job families. So when you have like 7 job families, then 60-65% is like fair enough, because there's a lot of confusion between like software developer and data engineer, machine learning engineer and data scientist, product manager and business analyst, so around that. So this was one of the examples, and now we can talk about the coding aspect of it.
Hello, I have one question. How is the graph convolution is implemented? Because different nodes may have different numbers of neighbors.
Correct. So it depends on like how you train your model. So one is like if you're doing like a graph prediction task, then your training data set has like individual graphs as inputs, right? So then you, I'll show you in the code like how you define your graph, and then uh, I think it will be easier.
Thank you.
Yep. So this is like the PyTorch documentation which I have been talking about recently. So they have like a lot of collab notebooks, which from where you can at least have a baseline code for doing a lot of stuff. So even for like our assignments and projects, we used to just start from here. So if we go to this one, like node level prediction task, so they kind of do a good job. They will do it like a naive way, using a simple perceptron method or something like that, using a conventional neural network, and then they will do exactly the same thing with graph neural network, just to compare between the results, right? So right. So in this data set, they use a data set called Cora, which is like a citation network data, like 2 sites zone. So initially what they do is like they represent each node as a 1,433 dimensional vector. Just like you mentioned, like we could have like a 1D dimension representation of everything, and then we can just build a solution around it. So that's what they try to convey here. So they trained the model using a regular structure, and then they did like a multi-layer perceptron, and then they get certain accuracy. Like they talk about accuracy of that. Yeah, so they get like a 60% accuracy on test data set, and then they translate the problem statement into a graph neural network where certain words coexist or not exist, so they have an edge or not, right? And then they do it. They don't even do a lot of stuff. So they have like one convolutional layer, 2 convolution layers, and 1 ReLU in between them. So that's it. So even with this, they are able to generate 80% accuracy. So that's like a huge gain, right? So that's like how they motivate people into using this library. So the way to go about this, the code is, so they have, So you just have to check like the input structure. So input structure asks you for three things. I can go back to the documentation. They have a nice documentation around it. So we talk about something. Right. So only these are the attributes which you have to care about when it comes to input data. Like how many features does your graph have? Like input nodes and how the edges are defined. Like if you have like 100 nodes, not all of them would be connected to one another, right? That's like a max of how many you can have. But then using the edge index attribute, you kind of convey the tuples around like one is connected to 2, one is connected to 3, one is not one. If there is no value like 1 comma 4, it means one is not connected to 4. So this way you define your edges, and then you can define your edge attributes like we talked about TF-IDF score and all this stuff. Then you can define your labels. So if it's like a graph level prediction task, then you will only have one label. But if it's like a node level prediction task, then you will have n y values if you have like n nodes in the data, input data. And then the position index is like, because even if you have like values on a different scale, you need to define the positions because a matrix will operate in like indexes, right? So then you just define the position index of it. So then they take like this small example of like if 0 is connected to 1, 1 is connected to 2, this is how the edge indexes will look like. So any data you have, you just need to translate into this kind of format so that you have your data set. And then just like any other PyTorch based solution where you have like a data loader and create data set utility, over there you can load like a batch of examples. You can define the batch size, mini batch size, and then you can just train the model. They have mini batch size, which is really good because right now I'm working on a project which has around 1 million nodes in the data, filtered from 2.2 billion nodes. So to train that model, you need RAM, which is more than 1 terabyte, which is not possible. Right? So we use like mini batches to run the model. So I'll suggest like you guys pick up any sample data set from here. I was planning to share data sets from my assignment, but someone told me that you can't really share assignment stuff because it's like copyright to that professor, right? So otherwise I would have shared that Amazon dataset, which is really nice, like click-through rate and all this. But even here they have a lot of datasets around chemical molecules, citation Reddit data, and all this. From there you can actually start working on it. Yeah, so this is, and they have a lot of examples. And the thing I talked about GNN explainability. So they have a direct utility like explain. So within explain, you feed your model and the input node or whatever you want to predict, and it gives you a nice explanation of why a certain explanation was made. Kind of makes it like a one-stop solution. And with like ChatGPT, you can ask, maybe it can write the code for you. So this is like a high-level overview of GNNs in general. So I also have like limited knowledge of what I've learned in last 1 year. So I could be wrong on certain points, but the whole idea is to convey that there exists a machine learning approach using which you can actually harness graph structures to do a lot of machine learning tasks. If you guys have any questions, you can reach out to me later as well.
Can we configure this graph? Like we also have this, like in normal, we also have this randomized CD. So is there something like where we can tune the graph itself as a parameter?
Graph itself or the
Graph
architecture
structure,
of the graph?
architecture of the graph.
Yeah,
if
so
possible?
there is a thing called graph architecture search, using which you can define how many layers you should have, how many aggregation layers you should have, and all this stuff. But if the data set is big, if the graphs are big, then they take a lot of time. So generally, people go by cut. 2 to 3 layers is good enough. Like I've seen, like after a certain while, if you keep adding attention layers or whatever you add, it doesn't add any value to your graph structure unless you add more features.
So, like we still have to do the data exploration. We
Oh
can't
no,
just-
so no data exploration is required, right? You just need to know in your mind like how the graph should look like. Yeah, like because in that class, some people try to predict the smell of a perfume uh, using the ingredients. So they created a graph of ingredients and then they did. I don't know like how the accuracy and all those, but that was one of the ideas where they tried to predict smell of the perfume. So, any questions?
we can probably ask them to do one. Have you guys used Collab before? I hope so.
Yeah.
Okay, so we can.
Yeah, so everyone if has laptop, they can just maybe try on Collab once. And if you have like doubts on like very basic things like what are this edge index or all those things, so we can help you resolve those things. Because unless I'm pretty sure like if you guys don't launch a collab session here, you probably won't do it later as well. So it's probably good to do it here once. And yeah, one announcement. So we are also thinking of working on 2 Kaggle competitions. So if anyone is interested in collaborating, he can just email us. We can reach out to.
GRIDS
How do
USC at
they-
Yeah.
Yeah, just did. 3 days. And I did 2 tokens, and I used the bonus. I did a bonus point. So then and then I got a ditch 5%. And it was basically that. Did you submit on time?
Yeah.
Did you submit on time?
So we'll be sharing the Google Collab link with you, where we can just go through the example.
Oh. Have you tried it? Yeah, I'm just checking out. Yeah. I got scared. Yeah, that's exactly.
the
Bulgarian?
the images.
The last
And they use it. You know what I went, she does it, they didn't even know. Especially with the back information.
Oh no, I think. Oh yeah, right. Passport.
Yeah. Very complicated. I actually did part of it. Actually, I did the image part. They just didn't even use it. I gave the network and got 40% without even using the image. Like, because you know, you just want to scan it layer, you don't need to have MPID.
Yeah, it is for.
That's not it, that's I got the DW.
You know what I just want to say? I'm going to guide the dates. And that yeah, so we have 5 more. This was our 6th patient. Yeah. Oh yeah. I'm pretty sure to make sure.
Can you just send the email to you guys so you can check your email? It should be from GRIDS.
Let me make sure it's in. Hey, done it. Oh.
Is that for the material?
No, this is.
I'll send it. Green, I'm not sure anymore.
No.
You didn't get it. Like, did you register for online and came in person?
I had selected local as in person. It's just for the online.
Oh, yeah.
So it is part of it.
So, you got it? You got it.
Yeah, this is like my own.
Is NKY certificate.
Yeah, so
That's what it is.
I just thought we can
Yeah.
You got it. You send it to them. It's dispute process.
MY.
Oh, he was not there.
Yeah,
I'll send it on
MY.
Alright.
What's her name?
Yep. Like nothing.
That's
Your last name?
Okay.
Don't even your last name. It seems like there isn't a particular rule. Is there anything that you don't see that you see?
No, it's fine. It's fine.
Submitting your project.
I'll be there 10 hours.
And guys, so this is like a sample way of how you can translate Tableau data into a graph structure. So we talked about the job description thing, right? So here you can see like individual graph ID, which is like 0 to the number of 3, 4, 3, 6. These are all like individual job IDs, and then the node IDs are IDs allocated to unique skills like Python, Java, and all this stuff. So in the raw structure, you have like any skill which occurs with another skill becomes a row, right? But then you translate into edges. So then you just have to write a basic code of like the directed edges, where you define that if 401 comes with 402, then you define an edge between those two indexes. It's something like this. So once you have that, then you can just generate a graph here. I mean, if you want to train on GPU, then you do everything on torch. Otherwise, you do on. So if you see here, yep. So if you see here, we define data object where you just define whatever all the nodes, which is like list of all the skills which occur, and then what are the edges, and edges are coming from the structure we created above, edge list. Edge list is created using like if two nodes co-occur, then they have edge between them. Then you define the edge index, and then Y is like what job family they belong to, something like this, and then indexes. So then you return the data. So this essentially is one graph for you, generate graph function. And then you can run it over on all the graph IDs to generate a data list. Now this list has individual graphs within them, and then you just shuffle just for sanity, and then you can use you can use data loader, which is a typical functionality in PyTorch, where you can define a certain set as training and test. So data list is essentially a list of all the graphs, and then you can define your batch size here, if you want to shuffle or not, and all these things. And then this is a checkpoint, and then this is like the architecture. It's a very simple one, like convolutional layer followed by three attention layers, and then a linear layer, and in between them a rail. Global max pooling because global mean pooling because you have to extract the embedding of the graph. Like in our case, we had to do a similarity. So we at the second last here, we just see how the entire representation of graph looks like. So we kind of aggregate all nodes representation into a single representation. So using a mean pooling method. And then you can just train the model. So the whole point of showing this small thing was like if you have a tabular data, it's pretty easy to translate everything into graph. The only thing is you need to know what your features will look like, what your edges will look like. And once you have that, then I think it's pretty easy afterwards. But yeah, for us it took a while to actually go from here to the graph structure because in our case, it's like an undirected graph, right? If Python is connected to Java, Java is also connected to Python in a graph, right? But in some cases, it's not the case. So we had to like accept the fact that for us, it's going to be an undirected graph. And to create this, we actually leveraged the graph prediction code which they have shared, so that we didn't have to write the graph class ourselves. We just added a few layers and then just fed in the input data structure in the required manner.
Want to show the example?
The collab one, is everyone working on some collab example?
The second example.
Okay.
Or we can just go give a brief overview. Because you have to close in 5 minutes. This is a class.
No, that's my project.
You have to follow him on here.
But yeah, it's kind of a copy of node classification notebook, which we just shared with you guys. But the dataset I'm more familiar with, so I just leverage the dataset. So, like, if someone is really interested to actually use this node, which we share. Yeah, so the way to go about it is like they have this input dataset. So you just have to explore this dataset without actually converting it into a graph to see like what all information it has and how the transitions are happening from converting the tabular data into the graph structure. And then you should do it by yourself without using like because they definitely have the graph structure within this object, this plain-toed object. But you should convert it yourself so that you know how to convert a tabular structure into a graph structure and learn about how to define edge indexes, how to define nodes and everything. Because once you have that, then it's just as simple as using any other neural network structure. Because over here they use a multi-layer perceptron. So they kind of use a regular structure, unlike a graph. So you can see how the data structure looks like. And then they also transition from graph, regular to graph. From there you can see how the data set now looks like. And then you can think of a lot of problem statements, like if you pick up research paper, 100 research papers, and then they have citations. So you can create a graph of citations, right? And then you can think about uh, if certain if certain papers should have cited someone or not, because sometimes we miss out certain citations. So a simpler approach could be you can extract tweets and then who commented on those tweets, and then you can extract virality of a tweet using graph structure, because someone may not follow me who tweets, someone retweets and all those things. So it kind of becomes a tweet structure. So I'm just like throwing in some raw ideas, like, so that it can work on any project.
I have a doubt. I have very limited knowledge on neural networks, but I just said like you might follow someone and you might not, and they might not follow you back, right? So in a graph structure, there might be bidirectional connection between nodes, and there are also possibility that two nodes are connected in only one direction. So how are you going to apply this neural networks and lay it into that?
Right. So when you define edges, you just have to tell if node 1, an edge goes from x to y, and then you have to tell if a y to x node edge exists or not.
That's how we define graph. Okay.
Correct.
So, but when in the context of neural networks, so when we need to, I don't know what to call it. We'll do something called layering, right, by using weights.
Right.
So you get the accurate data.
Correct.
So, so how is that possible? In context of neural networks, everything is connected, but here in the graph, there are some bidirectional connections and there are some unidirectional connections. So
Yeah, so maybe you are confusing it with like a regular CNN or something, where the structure is very defined, like it has to have 128 pixels across 3 channels.
comparing it with the CNN, yes.
Correct. So it's like a static structure, but here the torch geometric library knows that every individual graph will have a different number of nodes and edges. So it's not. So in this, when you define this, when you define this GCN, you nowhere tell how many features it has, like X. You don't tell it, because for it every graph is an input to it. Something like that. But yeah, if you read about documentation, you might know better. So I think that is all for today. Thank you all for coming.
Thank you so much.